ones, and it might have some exceptions, but it's not going to be like only the super hardest question I can think up. So that's a good question, though. All right. So the reason this happens is because if you have a 3D orbital and it's full, that's a lot more stable than having a half-filled 4s orbital. Also, the 4s orbital will lose one of the electrons to the 3D orbital because when that happens, there's something that happens with the energy, and the energy levels there adjust slightly so that it's just more favorable for the electrons to be in the 3D orbital. Now, that happens kind of in the middle of the transition metals, and then right over when you get close to the end of the transition metals. So if you look down below, we'll get back to the lead here in just a second. If you look down below that at chromium, you see chromium is, the end of chromium is 4s1 3d5. So it would have been 4s2 3d4, but if you half fill the d orbital, that's more stable. And then it's the same thing with copper, because it would have been 4s2 3d9, but they're so close to a full d orbital that one of the electrons will just go into the d instead of filling up the s. Because a d is, when I say d orbital, I mean d subshell. The d subshell is so much larger than the s subshell that when you fill it, or even half fill it, it's a lot more stable than even a full s subshell. How does that happen? That is a good question. So what happens? Do you mean how does it happen that it's more stable, or how does it happen that that electron goes up to the next level? Both. Okay, that's a good question. All right, so it's more stable just because the d orbital, not orbital, d subshell is so much larger. It's able to hold 10 electrons. And when you have something that large that's full, it just is very, very stable. When you have a subshell that's full, that's a stable situation. And the larger the subshell, the more stable it gets. So does that mean when changing the configuration of an ion of one of those elements, instead of affecting the s orbital, first it would affect the d orbital? You would think, right? Because you're going to remove it from the higher energy level. But it's odd in these situations, because when you fill them up, a lot of times one of the electrons will go from the s orbital to the d orbital to try to get it half full, or to try to get it completely full. If you go to the periodic table notes that I showed you last time, there's a periodic table that has all of the transition metals labeled with the end of their electron configuration, and looking at that, you can get the pattern that's going on with them. But actually, when you have an ion and you're removing electrons from an ion, so when you have an ion, the first thing you do is write out the neutral electron configuration. And then if you have a positive ion, you're going to remove electrons from the highest n level. Only if you're really close to having it be full. So let me see if I can show you that periodic table real quick. Actually, I should have stayed on that page. Just need to go to the top of that page. All right, let's go back one page. And then you can go back that far. Okay. All right, so this right here with the periodic table and electron configuration stuff, know if I like that one better or the other one. I'll try to make this a little larger so that you can see it a little bit. So if you look over at number 21, which is scandium, I think, and then titanium. So that one right there at the very beginning is normal. It's exactly what you would expect. Let's see. So past a certain point, the d orbital will take, yes, past a certain point, it will take one of the s orbitals because it's so close to such a stable state. When it's full, it's very stable. And when it's half full, it's very stable. Technically, no, they're not in an excited state. What happens is there's a slight shift in the 4s and the 3d. When they get to that level, they kind of switch. So before the 4s was slightly lower, but when it gets to that situation where the D subshell is half full or completely full compared to a half-filled s orbital, they switch places. So the D subshell, when it's full, goes down a little bit in energy. They actually still they don't violate any rules. So they don't violate the Aufbau principle that says you're filling the lowest energy ones first, because the D subshell will actually decrease in energy at that point, making it the lower energy. But normally, the 4s is lower. And then why would the promote the s2 electrons to the d orbital, make it half full? Let me take a look at that. That's a good question on that. So if you look in column 5B or column 5 there, you see vanadium, it's got a 3D3 and 4s2. And beneath that, you've got 4D3, 5s2. So those, up until you get to about the third one, they behave exactly like you would expect. And the reason, because when it's 3D, when you have a D subshell and 3 of the orbitals have 1 electron in it, it's almost stable enough to pull one from the 4s, but not quite. Once you get up to chromium, you would expect it to be, since vanadium was 3D3, 4s2, you would expect chromium to be 3D4, 4s2. But being a 3D4 would be so close to being stable that it will actually decrease the energy of the whole system if it promotes an electron from the 4s to the 3D. So the goal is to either get it half full or completely full. So looking at the exceptions, once you get to where you would have a D4, it promotes 1 to make a D5. So you can see that chromium and molybdenum. And then manganese is already a D5. And so you go over to iron and it's D6. So it's not enough to promote to the next level. And then the same thing with the D7 and the D8. Now this is the top row. But the D9 becomes a D10, and D10 obviously becomes the same. But when you move down a level, move down a period, so you're looking at ruthenium and rhodium and palladium and all that kind of stuff, it goes 45, and then 45 again, because 43 is actually in the middle. And then ruthenium is a D7. If you look above that, iron is a D6. So it has to do with a lot of different energetics that we're not going to completely get into. But I guess the best way to explain it is depending on how many energy levels there are, like how far away from the nucleus the electrons are, as to whether or not the electrons are going to kind of switch from one place to another. Let's see. So a d orbital subshell at 9, hypothetical reason, it would take 1 out of, yes, that is correct, Aaron. And then how do we know how many unpaired electrons an atom has based on its electron configuration? For that one, you have to draw out the orbital diagram, and then you just count the ones that aren't paired. And I'll do an example of that in just a couple minutes. And then what about 8b, 8, 9, and 10? Because iron, cobalt, and nickel have 4s2, but ruthenium and rhodium have 5s1. Yeah, that one is one that gets kind of deeper into the energetics that we're not going to quite cover in this class. It takes a really long, like many classes to explain that. But it has a little bit to do with the fact that when you get into the next period, the electrons are further from the nucleus. And then Hirsch says because it goes, okay. And then does that say 4s45, 5s2 become more stable? Yes, they do become more stable. To fill the seats, exactly, Hunter, you are correct. The thing is that in this case, it's almost like you have seats on a train track and they move. So when you get the bus half full, some of the seats shift places. And instead of having the 3D being higher in energy, all of a sudden it becomes lower in energy. So you're still filling them from lowest to highest, but the 4D and the 3S, that's backwards. The 4S and 3D switch when you get close to a half-filled orbital, and then again when you get close to a full orbital. And the ones that aren't paired, the only ones, yes, the ones that are not paired are the ones with a single arrow in a blank. And okay, all right. So let me do some examples because I think that'll make it a little bit more clear on how to do some of these. To do that, I'm going to switch to my iPad. So I'm going to disappear for a second, and then I will be right back. Sure, absolutely. I will be glad to do one of those. I will be right back.